Now, in second order partial derivatives, it is simply saying that the first order partial derivatives are being differentiated again. Now, examples of second order partial derivative could be, let's assume that we are given the volume of a cylinder. V is equals to pi r square h, and we are asked to evaluate its second order partial derivatives. That is 1. They are in 4 forms of second order partial derivative: partial derivative squared, the r squared, the squared v, the h squared, the square v, the r with the h, and the square v, the h, the r. Now, let's begin with the square v, the r squared. Now, the square v, the r squared is simply differentiating with respect to r of the v, the r. Now, let us evaluate our dv dr, and this we have done in our previous videos. That dv dr will be h as a constant, sorry, pi h as a constant, and differentiated with respect to r of r squared, and this will give us pi h multiplied by 2r and this will be 2 pi rh. Now, the square v, the r squared, which is partial derivative with respect to r of dv dr, and dv dr is 2 pi rh. Now, in this case, we know that we are differentiating with partial with respect to r. Then we can bring our 2 pi h as a constant out, and then differentiate fully r with respect to r, and this will have 2 pi h multiplied by 1. We'll have 2 pi h. Let's take the next one. Let's evaluate the square v, the h squared, and the square v, the h squared is differentiating partially with respect to h of the v, the h. Now, the first thing to do is to evaluate the v, the h, partial derivative of v with respect to h, and that is d dh of pi r square h. Now, since we are differentiating partial with respect to h, all other things are kept constant, and that will give us pi r squared, and then we are differentiating fully with respect to h of h, and this is pi r squared multiplied by 1, and this will give us pi r squared. Now, let's differentiate again with respect to h. That's d dh of pi r squared. Now, in this case, we are differentiating partial with respect to h, and every other thing is kept constant, and then we are going to differentiate fully of 1, and this will give us pi r squared multiplied by 0, and this will give us 0. The third one which says d square v dr dh. The square v dr dh is differentiating partially with respect to r of dv dh. And let us make our substitutions, right? Our dv dh, which is this, is pi r squared. That's d dr of pi r squared. Now in this case, our pi is a constant, and that will be pi multiplied by full differentiation of r squared with respect to r, and this will give us pi multiplied by 2r, and we'll have 2 pi r. Third one, which is the square v dh dr, which is partial derivative with respect to h of dv dr. Now, making our substitutions, right, we have our dr here, dv dr, which is 2 pi rh, 2 pi rh. Now, since we are differentiating partially with respect to h, all other things are assumed, are kept constant. So we have it to be 2 pi r, and full differentiation with respect to h of h, and we have 2 pi r multiplied by 1, and we have 2 pi r. Now we notice something, that this is equal to this. Therefore, it can be saying that d square v dr dh is equals to d square v dh dr. Let's take another example to this effect. Number 2. Given that z is equal to 4x squared y raised to power 3 minus 2x cubed plus 7y squared, and we are asked to evaluate d square z, the x squared, d square z, the y squared, d square z, the x dy, d square z, dy dx. As we all know, the first thing to evaluate are both dz, dx, and dz, dy. Fundamentals. So let's evaluate dz, dx. That means we are differentiating partially with respect to x. Therefore, our y is kept constant. So let's begin. Of 4x squared y cubed minus d dx of 2x cubed plus d dx of 7y squared. Now, if our y is kept constant, so we have 4y cubed with a full differentiation with respect to x of x squared, and 2 with a full differentiation with respect to x of x cubed plus 7y squared with a full differentiation with respect to x of 1. And simplifying this, we will have 4y cubed multiplied by 2x minus 2 into 3x squared plus 7y squared into 0. And with our dx, dy, dz, dx will be 8xy cubed minus 6x squared. You can pause the video now and evaluate for dz, dy. And that is d dy of 4x squared y cubed minus d dy of 2x cubed plus d dy of 7y squared. Since we are differentiating partially with respect to y, our x is kept constant. So we have 4x squared d dx of y cubed minus 2x cubed of d dx of 1 plus 1 plus 7y squared plus 7 of d dy. This is y of d dy of y squared. Now we have 4x squared multiplied by 3y squared minus 2x cubed multiplied by 0 plus 7 multiplied by 2y, and we will be having 12x squared y squared. This nullifies to give 0 plus 14y. So let's begin with evaluating the first question. That's the square z dx squared, and that is partial derivative with respect to x of dz dx, and this is d dx of our answer here, 8x y cubed minus 6x squared. So differentiating this now, let's bring our y as constant. So we have 8y cubed, and we differentiate fully of x minus 6, and we differentiate fully of x squared. So we have 8y cubed multiplying 1 and 6 multiplying 2x, and our answer will be 8y cubed minus 12x. Next, we are asked to evaluate the square z dy squared, and this is d dy of dz dy, and that is d dy of 12x squared y squared plus 14y. Now, since we are differentiating partially with respect to y, our x is assumed constant. That will give us 12x squared, and we fully differentiate our y squared plus 14 and full differentiation of y. So we have 12x squared multiplied by 2y plus 14 multiplied by 1, and our answer will be 24x squared y plus 14. Thirdly, the square z dx dy, and this is partial derivative with respect to x of dz dy, and our dz dy given as calculated is this 12x squared y squared plus 14y. Now, when we are differentiating this, we understand that our y is kept constant. So we have 12y squared with a full differentiation of x squared plus 14y with a full differentiation of 1. and that will give us 12 y squared multiplied by 2x plus 14y multiplied by 0. This gives us 0, and our final answer will be 24x y squared. And finally, let's do the same for d squared z dy dx. d squared z dy dx is d dy of dz dx. Now, after this is done, we take our d dy and our dz dx as evaluated is 8xy cubed minus 6x squared. 8xy cubed minus 6x squared. And since we are differentiating partially with respect to y, our x is kept constant. d dy of y cubed minus 6x squared and d dy of 1. So we have 8 multiplying 3y squared minus 6x squared multiplying 0. And with this, we will be left with 24x y squared. Just as we saw in the first example, that our d squared z, our d squared v dr, in the first example, that this form of differentiation are equal is the same that we are seeing here. So therefore we can come to a conclusion that d squared z dx dy is the same thing as d squared z dy dx.